Hello there. Today we are going to discuss this very special topic called as differential amplifier. So in earlier modules, we have covered a single stage amplifiers, or rather we would say single input amplifier. Okay. And we have seen all the configurations such as common base, common collector, and common emitter using a transistor, and they were all single-ended input amplifiers. For example, you had this positive V supply, and then you had this resistor, and then there was this BJT, and which is used like this, let's say transistor Q, and we used to take output from this collector, and this is N, P, N of the transistor. Then through some bias, you apply a base voltage through this to the base of the transistor. The resistor at the emitter to the ground is called as resistor RE. That was called as emitter degeneration resistor. Okay. And this resistor was there to provide the bias stability and and also the stability against the transistor parameters. And we just said that the output divided by the input of this amplifier, that was the gain, was approximately GM times RC. Here it was your collector resistor, right? And with the emitter resistor, we got the improved formula for the gain that we can rate. This is the gain without the emitter resistor. And with the gain, let me write, your gain was about, just a minute. So it was about RC over RE. So you see that the gain of this transistor was independent of the transistor transconductance, which has variations, and therefore the gain is likely to vary. So to provide the bias stability and the uh, stability against the intrinsic parameter variations, we use this emitter degeneration, which sort of provides the negative feedback in the amplifier. And we got this expression of the gain, which is set by Mayer ratio of the two resistors. Now, coming back to our discussion, we are talking about differential amplifier. So instead of single input in this amplifier, now we will have two inputs. We will make the full circuit. So what you see here, we have V plus and V minus, which are applied to the positive and the negative pin of this amplifier with a gain A. The Vs plus and Vs minus are the two positive and the negative supply voltages, and V out is the output of this amplifier. So differential amplifier is primarily used as a first block in operational amplifiers, comparators, audio amplifiers, and so many other circuitries that you will come across. So why differential amplifier, and why it is preferred over single input amplifiers such as this one? So obviously the answer is the noise or the common mode signal. Differential amplifier has the ability to cancel to the first order noise introduced to the signal, to which is coupled to the inputs of the amplifier. So let us say how. So for example, you can write output of this amplifier is gain multiplied by the input. But this time your input is the VID, which is the difference between the two inputs. Okay. In this stage, you simply write VO equal to gain times VI. Whatever the VI you apply here, that multiplies with the gain of the transistor circuit. Here also the same formula, but the difference is this time you have two inputs, and amplifier, differential amplifier will amplify the difference between the two inputs. And that's why this formula. So let's say you have like 500 millivolts at the positive pin, and then you have like 300 millivolts at the negative pin. So the difference VID would be equal to 200 millivolts, right? And if you have a gain of the amplifier, which is 10, for example, so therefore your V out would be equal to 200 multiplied by 10, that is 2 volts, right? So this is how your differential amplifier will work. Now, there is, so the definition is your differential amplifier amplifies the difference between the two inputs. Similarly, it is used to reject the common mode signal. That means the signals which are common to both the inputs. Let's, for example, a noise or a DC level from the previous stage of the circuit that gets coupled to both the inputs simultaneously, or the noise signal that gets coupled to both the inputs simultaneously. So in that case, the magnitude of the signal is common to both the inputs, and ideally your amplifier should have zero output, because signals magnitude are same, so their differences is initially zero. So you can say that there is a final output expression, which is V out is equal to AD times VID, which is the output due to differential inputs, and this term is the output due to common mode signal, where output is given as gain multiplied by the average of the common mode signal, that is V in plus minus V in divided by 2, and AD is the differential gain, AC is the common mode gain. In the ideal situation, output due to common mode signal is 0. Therefore, you only have this expression available to your disposal. So if your differential amplifier is so good that it provides a zero common mode gain and very high differential gain, then you have new term called as common mode rejection ratio, CMRR, which can be expressed as 10 log of 10 in bracket AD over AC whole square. And in its simplified form, you can simply take the 20 logarithm 10 and the ratio of the two gains, differential gain divided by the mod of common mode gain. Okay, so let's say you will have 20 log of 10 and differential gain is 100 and the common mode gain is 1. So you simply take 20 log of 10, 100. So that's how you can get the differential amplifier CMRR. Now moving on to our next slide, what you see here, let me use the eraser first. There is a lot of flexibility in using how you want to use the differential amplifier. For example, you can see a differential amplifier can be with the differential inputs, as you can see right over here, or in the previous module, previous slide, we see that you have positive and the negative pins. So you have input 1 and you have input 2, and then you take the output. So you can have a differential inputs and differential outputs as well. So instead of one output, you can have two outputs. So you now see how I am converting this circuit from single-ended inputs to and single-ended output to the circuit with two inputs and two outputs. So V in plus and V in minus are two inputs, and V out is basically can be written as VO1 minus VO2, where VO1 is the output at the collector of this transistor and VO2 is the output at the you just take a mod of it at the output of the collector of transistor Q2. So because of the differential input and differential output arrangement, you are expecting a higher gain than your single-ended version of the transistor amplifier. And also CMRR is very high in differential amplifier as compared to single-ended amplifiers right here. There is an option, however, you can also use a single-ended output. But in this case, your gain is half. If you use this circuit, you can see you can just take the output from one of the collectors of the transistors and you still have differential inputs. But in this case, your gain, differential gain will be half the total gain that would have been possible if you use the differential outputs. However, there is arrangement to maintain the same gain, not this one, rather you maintain the same differential gain that you can get if you use the differential outputs as before. So arrangement for that is to you replace these resistor RC1 and RC2 by means of an active load. So active load implemented by a simple current mirror circuit. We have seen a lot of exercises in our previous models. So if you are new to this, refer to those models using current mirrors, using BJT, using MOSFETs, using NMOS transistor, using PMOS transistor, using NPN transistor, and using PNP transistor. So what you see here, you basically are using the Q1 and Q2, same as the two inputs, non-inverting input and the inverting inputs at the basis of the transistors, and their emitters are common connected here, and from there you have a constant current source. Towards the one end is connected to the emitter pin and another pin is connected to the negative supply, let's say minus VEE. Okay, and this is plus VDD or plus VCC. And then you still can now have single-ended output. However, the gain will be maintained as if you are using the differential output. So gain will be AD. So what you do here, you use the current mirror where, let's say this is your PNP transistor. This is P and P. This is P and P. And this is your emitter of the transistor. Let me use a different color here. So that's your emitter right here. That's your base. And that's your collectors of the transistor. So you basically can see that your VEB is equal to, for the transistor, let's say Q3, and this is your transistor Q4. So VEB will be equal to VEC. This is for the transistor Q3, okay? And this is possible because you have shorted the collector and the base pin of the Q3 transistor. That makes the transistor always operate in the linear region. That is the region right to this line. This is your linear region where the current is constant. Okay, because of this arrangement, you don't let the transistor saturate. This is your saturation region. This is your linear or active region. Okay, and with that, it provides you a constant collector current that will flow through the transistor Q1. And because of this, assuming the transistor of same type, same size, this current IC1 gets mirrored into the transistor Q4, which is supplying the transistor to the transistor Q2. Okay, so these currents are coming right from Q3 and Q4 to the Q1 and Q2. And since the emitter is common to that, your IE is equal to IC1 plus IC2. So this is how you can do the analysis of the circuit. So similarly, the same analysis apply to this circuit. So finally, you can also use a single-ended input. You just keep it ground, just make the one of the input of the differential amplifier to the ground and apply your signal to the remaining input. And then in that case, it acts as this kind of amplifier. You see that. But you still have an advantage of taking a differential output or single-ended output depending on your choice. So you see there are a lot of versatility versatility and a lot of flexibility in using the differential amplifiers. So we move to next slide. And let me just clear all the drawing. Now let us understand how we will achieve a differential gain by doing some fundamental analysis right here. So we will recall our concept about biasing the BJT single-ended single input amplifiers. We will recall the concepts linked to the forward biasing and the reverse biasing of the transistor regions, right? And yeah, so we see here the circuit. I have this positive supply voltage VCC, and I'm using two transistor Q1 and Q2, and the two inputs are V in plus and V in minus, and there are pins like this. This is my NPN transistor. This is also NPN transistor. And let me also highlight the terminals. That is collector pin, this is base pin, and that's emitter pin. This is also a collector pin, this is base pin and the emitter. So emitter of both of these transistors are shorted together, as you can see that. And now, before I apply time varying signals, for example, I need to bias the base of these transistors Q1 and Q2. So I can apply a DC bias levels at both the base voltages, and let's say I would say that DC bias level is VB1, and here also I apply a DC bias level VB2. I call like that. Now base is at the positive, and here also base is at the positive. Now, in order for this differential amplifier to work as an amplifier, my transistor Q1 and Q2 must be biased in the active region. In other words, I can say that this is the common emitter configuration, obviously. This is again the emitter degeneration resistance that is helping me to provide the stability against the variations in the bias and the transistor intrinsic parameter variations due to temperature or some other effects or second order effects. So this is my VCE, and my curve of the transistor Q1 and Q2 should be like this, and I'm expecting right of this, the portion right to this dotted line is my linear region where I want to bias my transistor. So I choose an operating point, for example, here. So I would say this is my operating point right here. So this is my VCE max, and here somewhere I have IC max, right? And my biasing point, the IC that I'm flowing, letting flow in the transistor would be this one. Let me draw it properly. So here is my IC current, and this is my VC point. Okay, and that's my IC max here, this point. Okay, so with that assumption, the base emitter junction of the transistor should be forward bias, and collector base junction or base collector junction of the transistor should be reverse bias. So collector base junction should be reverse bias. Okay, so having said that, if I maintain the DC bias level at base 1 and base 2 of the transistor, this forces the bias current IE that is set by the resistor RE. Okay. to split equally between the two transistors, and that gives rise to the collector currents IC1 and IC2 of the transistor. So IE is basically IC1 and IC2 when I don't have any external input signal to be amplified. I just have the biasing. I applied the VB1 and VB2, and I have this resistor RE. I switched on the power supply, and I see that the IE gets split equally between the two transistors and IC1 and IC2. Now, what I want is this junction, this diode basically should be forward bias. Okay, and this diode should be reverse bias actually. So the voltage at the collector should be greater than the voltage at the base by 1 VBE to make this transistor always operate in the linear mode of operation. Same goes for the transistor Q2. Okay, now let's say I apply a differential signal to this transistor. So let me draw it properly. What I'll do is I will say that I apply the signal levels like this. There is this small AC signal, let's say delta V, or rather I would say this is an AC signal, VAC, and that is superimposed over this DC bias level. And here also I am using a small AC signal VAC superimposed over the bias too. So now my differential signals applied to the basis of the transistor will be VB1 plus delta V and VB2 minus delta V, because it is the V in positive and it is V in negative. So the one signal over the DC level, let's say this is my DC level VB1, and the signal goes up to this signal to over this bias level, and here also my VB2, and here the signal goes down right here. Okay, and this is up down. So they are opposite phases signals. So one signal increases here and the second signal decreases, because that's why I'm saying the differential signal, they are same magnitude but opposite direction. One is positive, one is negative. So now because of this voltage levels, Q1 conducts a little more, because you have the base voltage increment that rises the base current, therefore that rises collector current. And for the Q2, the base voltage decreases by the amount VB2 minus delta V. That makes the Q2 less conducting, so the base current will be less, collector current will be less. And here I would say IC1 is greater than IC2. And therefore, the VC1, the voltage at the collector of the transistor, and the voltage at the collector of the transistor 2, the VC1 will go up and VC2 will go, in opposite way. VC1 will go down and VC2 will go up, as we can see here. Okay. So because you have more IC here, so there'll be a more drop across the resistor RC1. Therefore, VC1 is going down and VC2 will go up. Okay, all right. So we are going good here. Next, we can come back to explaining. And that's how you can see now you have this differential gain now. And output will be V out will be equal to VC1 minus VC2. Take a magnitude of it. Okay, so since VC1 is down and VC1 is up, you have a difference and multiply it with the gain, differential gain of the transistor. That's why V out will be higher and your signals will be amplified. So that's why this is the concept of how you get the differential gain. Now coming back to common mode gain. So what you see here, same circuit, and this time you have the signal applied common to your inputs. But now you say again, I have AC signal and there is a DC bias level VB1. And here also you have AC signal and I have a DC bias level VB. Rather, I would say VB, and this is also VB, because VB1 is equal to VB2 is equal to VB, because the signal is common, is the same signal I'm applying. So now with that arrangement, you have a DC bias level VB, but on top of that, you have this positive going signal and this is negative going signal. So your voltage levels at the bases are VB1 plus delta V and VB2 plus delta V. Both are increasing. This is also going up. This is also going up. So when this goes down, this is also going down. So in that case, your conduction level of the transistor is not changing, because when your base voltages are increasing simultaneously, your base currents are increasing, your collector currents are increasing, and hence your emitter current are increasing, the drop across the RE are increasing, and the emitter voltage is also increasing. So the VBE1 and the VBE2 remaining constant, okay, with the sinusoidal variations of the inputs at both the pins, base pins of the transistors, okay. And you would say that your collector current IE, your emitter current IE remain constant, and it is equally splitted between the two collector currents. So that's why you say IC1 is equal to IC2, approximately I by 2, neglecting the base pin currents of the transistors. And therefore, your VC1 and VC2 are varying by the same amount. Okay, so there is no difference between the two output signal levels, and essentially then you have you basically have the gain, which is common mode gain, and this is VC1 plus VC2 divided by 2, right? You basically will have some output, but ideally you will have this kind of things. You have VC1 and VC2 will be of same magnitude, so the output will be 0, ideally. But in practical case, you will have such level of the signals, okay? So hope you understood the concept of your common mode gain and the differential mode gain. In the differential amplifier, you also understood what the differential amplifier is and how it works and what's its comparison with the single-ended, single input amplifiers. So stay in touch.